Hello Panthers, video number 1 did successfully record, Christmas miracle. We're going to work on video number 2 here. So we're going to talk about trends in the periodic table which come about because of these orbital diagrams and everything else. And there's 3 primary trends that we want to look at. The radius of the atoms, the radius of ions, and then a trend called the ionization energy. And we can use the periodic properties, the fact that things sort of vary smoothly across the periodic table and repeat because of the shell structure. We can use them to understand trends in the periodic across the periodic table. So let's start with radius. This guy right here is what's called an STM, scanning tunneling microscopy. I mentioned this quite a while ago. It's a way of looking at atoms on a surface. It's a kind of a high-tech microscope. This one's actually from my lab at JMU. A student took this data, and this is a graphite lattice. So it's a piece of carbon that's actually in layers, and they've peeled one of the layers off and they've imaged this with the STM. So basically the way the STM works is a tip, got atoms on the surface, the tip scans across the surface and measures the electron density of the atoms down below. Now I haven't drawn this to scale because the tip is actually made out of atoms also. And so the atoms on the tip, which are metal, interact with the atoms on the surface, and it looks at electrons that are flowing between the two. Okay? So really important thing is every one of these bright spots represents a carbon atom. So the atomic radius is defined as the distance between the center of 2 atoms. Now for carbon, or for graphite, it turns out to be 0.246 nanometers. If you look at this scale, that's a 1 nanometer scale. So this is 1 nanometer this way, and it's 1 nanometer this way, which is kind of crazy when you think about it. Think about it, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 atoms you're seeing in a 1 nanometer space. This isn't the greatest image. If we did this really carefully, we would measure this to be 0.246 nanometers. Okay? That's how the atomic radius is defined, the distance between the center point of 2 atoms. Okay, so here's the trend on the periodic table. Now, this trend is pretty easy to understand. What we're going to talk about here is an understanding of where this trend is coming from. So the trend going down the periodic table is not very difficult to explain. Down the periodic table, the average radius gets larger. So just think about this for a minute. Why would the radius get larger as we go down the periodic table? Well, what do we know is happening? This is going from n equal to 1, 2, 3, 4, 5, 6. And remember what we said n is. N is the principal quantum number. N, the higher the n, the further away the electrons are allowed to be from the nucleus. The shells are getting filled further and further away from the nucleus, and they're larger. So it makes perfect sense that as we go down the periodic table, the size of the atoms should get larger. Okay? That trend is easy to understand. Increasing atomic radius as we go down the periodic table. What's maybe not so obvious to understand is as we go from right to left across the periodic table, the size also increases. Now, I think this is counterintuitive. Not obvious. Here's why I say this. So let's, instead of having these circles drawn on here, let me just sketch the periodic table. Something like this. So here's hydrogen, helium, lithium, beryllium. Actually, this needs to go this way, right? Boron, carbon, nitrogen, oxygen, fluorine, neon. Okay, so we've got 1 electron here, 2 here, 3 here, 4 here, 5, 6, 7, 8, 9, 10. All right, so across the first 2 rows of the periodic table, we go from 3 electrons to 10 electrons. Now your intuition might be, well, the more electrons I add, the bigger the atom should be. Doesn't that make sense? This one only has 3 electrons. This one has 10 electrons. So your intuition might be, well, look, as I go across that periodic table, the size should get larger because there's more and more electrons being added. The electrons want to be far away from each other because they're negative charges. Turns out that's wrong. Actually goes the other way. Lithium has a larger size than neon does. So if we want to understand that phenomena, we need to understand a concept called shielding. So what does shielding mean? Shielding means, we'll do this with a sketch. Let's take my lithium atom, since they're the two extremes across this periodic table. So lithium has 3 protons, so 3 plus charges in the middle. It's got 1s2 electrons, and then it's got a 2s1 electron. Neon, on the other hand, has 10 plus charges. It's also has 1s2, and it has 2s2. I'm trying to draw these close to each other, but not quite touching each other. 2p6. All right, so help me out here. Which ones are the core electrons for both lithium and neon? Yes, of course. The inner shell ones, the 1s2. So the core electrons interact the closest with the nucleus. They interact the most with the nucleus because they're closest to the nucleus. So if we look at lithium, we've got 3 plus charges in the nucleus, and then I've got 2 minus charges in the core electrons, and I've got another minus charge a little bit further out. This guy has 10 plus charges in the nucleus. It also has 2 negative charges in the core electrons, and then it's got 8 negative charges in the outer shell electrons. So what happens is the core electrons are effectively screening the charge of the nucleus from the outer shell electron. All right, let me say that again. The core electrons screen or shield, either term is correct, either shield or screen the outer shell electrons from the nucleus. And in lithium, we have 3 plus charges and 2 minus charges. They're almost equal. The number of pluses and minuses are almost the same for the core electron, or for the core electrons and the nucleus. So it's kind of like if you're playing a game of tag or something, or I'm a soccer coach. You're coaching soccer. You've got 3 players with the ball, and you've got 2 attacking those 3 players. Those are fairly even with one another. So the extra player that's further away is able to be shielded or screened from the 3 that are trying to get that extra player. In the case of neon, I now have 10 plus charges and only 2 electrons on the inner shell that are trying to shield the charge of those 10 electrons. And 2 against 10 are not very fair odds. So what happens is these outer shell electrons can feel the charge of the nucleus much more than the 1 electron in lithium can feel it. Let me say that again. Since there's the same number of shielding electrons in both of these atoms, lithium and neon, remember the core electrons are what do the shielding. Since there's the same number of core electrons, but neon has 10 plus charges and lithium only has 3 plus charges, the outer shell electron in lithium does not feel the nucleus as much as the outer shell electrons in neon do. So what's the effect? These electrons get pulled in towards the nucleus because they're feeling those plus 10 charges, or like plus 8 charges. Like the net result is this is like having 8 plus charges, and this one's like only having 1 plus charge. All right, so the 8 plus charges are able to pull these outer shell electrons in, which means it's a tighter sphere. So in other words, the atomic radius is smaller on the right side of the periodic table. Okay, because of this shielding or screening effect, all those outer shell electrons get pulled tighter into the nucleus. This guy here, this 2s electron, is kind of able to roam further from the nucleus without feeling its charge. Just like if this was a soccer team and you had 3 players against 2, but you had 1 extra player that was able to roam. This one, it's 10 players against 2, and those 10 are going to be able to start impacting the 8 players further out. Okay? Now, let me show you a graph of what this looks like. These are all the elements on the periodic. There's 2 different ways of showing it. One with sizes, one with a graph with the actual radius. You notice these are all helium, neon, argon, krypton, xenon. These are the noble gases. This is lithium, sodium, potassium, rubidium, cesium. You notice they're all getting larger as we go down the periodic table. That's not surprising. That's because N is getting larger. But as we go across each period, it gets smaller as we go across, and that's because of the shielding effect. Okay, that explains the atomic radius. So the trends are down the periodic table, increasing size, right to left across the periodic table, increasing size. The explanation going down is N is increasing. The reason why right to left is because of shielding of the nucleus, or the effective charge.